Hello, everyone. Thank you for joining our talk today. I am Himadri Pal. I'm software engineer and architect in Apple. Apache Iceberg is a very interesting project to me, and I'm sure it is to many of you as well. I have been an Apache Iceberg user for a long time, and recently I've started contributing to it as well. Jihan Ho, the co-presenter today, he needs no introduction. He is an Apache Iceberg and Apache Hive PMC. Jihan, say hi to everyone. Jihan is well known in the open source community as well. So we wanted to do this talk to spread awareness in the community about storage partition join or SPJ and its benefits in a data lake with Iceberg as a table format. With that, let's dive into the agenda today. So first, I'll talk about our journey to adopting Iceberg, then describe some use cases for SPJ. Jihan will then deep dive into the SPJ features and all the recent and future development in this space. I'll then walk you through an incremental process with Iceberg and SPJ. We'll then show the results of our experiment and share our learnings at the end. A primary motivator for adopting Iceberg was to facilitate a migration from a traditional and proprietary data warehouse to a modern data lake. End users of our data systems were familiar with the traditional RDBMS style operations in warehouse, and also pipeline producing these datasets we used upsert. So we wanted to maintain this style of interface when introducing the data lake. In particular, we had one pattern of data processing where incremental process continuously writes into a folder in Parquet. We call them journals, and a separate process periodically merges that data into the previous snapshot. With Iceberg, this process was much more efficient. Hive does support some level of partition override, but it does not support row level insert, update, delete. Using Iceberg from Spark, we are able to do insert, update, delete, and thereby reducing the second redundant process. Iceberg was also obvious to us given that Apple, it's available within the Apple. As Russell talked about in the keynote, a lot of active development is driven by Iceberg contributors within Apple. Finally, Apache Iceberg really works well with Apache Spark. As part of our migration, we ended up large amount of transactional data stored in a normalized form in Iceberg tables. A typical workload would then need to join a bunch of tables, project, window, and merge into an intermediate or final table. We'll then build a number of KPIs on top of these outputs. At our scale, these workloads were heavy on shuffle and heavy on memory due to shuffle and sort operations in the join. Some jobs would even fail. Partition pruning, addition filters can only reduce the shuffle, but it cannot completely eliminate. In certain cases, you don't have any partition or filter. So we also considered reducing shuffling by performing lookups against the dimensional data against NoSQL stores. However, this would have meant dealing with the cost of keeping the data in sync, as well as we have to invest in optimizing the NoSQL database for load and volume. SPJ, on the other hand, promises to eliminate shuffles with no additional cost and effort. So it became clear win for us. I'll now hand over to Jihan to understand how SPJ works and various enhancements since it was first developed. Over to you, Jihan.
Hi. Hi, everyone. Hi. So yeah, thanks, Himadri, for that. So I'm going to go into more of the technical part of SPJ. First of all, there's been some talks already diving into the technical side by Chow and Ryan, when the project first came out last year, I think by Chow and Anton as part of a general optimization talk. The reason we wanted to do another deep dive is that one, we've done a lot of new features for SPJ. We're really excited to share with everyone. And two, just a year or two in production, we realized that SPJ really is kind of the go-to optimization. Like, it's applicable in just so many places and has such a dramatic effect on resource and runtime that we just wanted to, again, deep dive to show how it works to everyone. So first of all, why is SPJ so useful everywhere? So as Himadri said, we need to look no further than the pipeline that Himadri was describing, right? He described several operations. One of them is the enrichment join. It's a traditional Spark join, between two data sets, and you do some processing to get some insights. On the other hand, the reason they moved to Iceberg is this upsert row level operations, right? Merge into target using source. The common thing between both of them is that if you look at the query plan, they're actually very similar, and in that they're dominated really by this huge join phase. If we can optimize that, we get a lot of savings. Yes, as Himaji mentioned, we always recommend to push down, filters and projections to the data source. That's all there, but a lot of times in the business use case, it's not practical to have, or it's not possible to have filters, right? You need data from both sides for the join or for the merge into, right? So that's why we really need to optimize this join. Another part is that whereas in the traditional join on the left side, you see the user could choose, outer, inner join, like it's explicit choice. For the Iceberg enabled merge into statement, there's no choice. It's implicitly a outer join because you need to actually process all the rows of target, even though they may not match, right? That's the contract of the merge into. And then when you have a when not matched clause, even worse, it becomes a full outer join, right? So processes even more data. So with great power, comes a lot more data getting processed. So let's just see how SPJ can help this and other use cases. So the idea for SPJ is really just to help this huge distributed join task. And so let's see how that's done. So the distributed joins really is just taking what you would join on one node, the algorithm on one node, and distributing it to many nodes or tasks. And actually the most expensive part, maybe surprisingly, is the distribution of the inputs for this whole algorithm. Basically, because it's an equijoin, you need to make sure that rows with the same join key map to the same task, right? And this is actually the cause of this infamous shuffle phase that Himaji mentioned, where we see a lot of jobs they either succeed well or they kind of don't make it due to lack of resource, right? So this is where SPJ really shines. This is so the alternative really is not a radical idea. It's that instead of doing the shuffle dynamically at the runtime, why don't, when you just make the table, already align all your data so that it's aligned by join key, right? Then it's kind of already shuffled by that time, right? So that's really the essence of SPJ. It's really no big radical innovation there. One thing to note about SPJ though is that it's really not a join algorithm per se. I've seen some confusion about that. After SPJ is only dealing with the inputs of the join. Afterwards, you still need to choose a join algorithm inside each task. So that could be either sort merge join or shuffle hash join in the case of Spark. And that also has some performance ramification, which I'll get into a little later as well. So going back to SPJ though, like the origins of it. So again, this idea is not new. So when the distributed systems came out, like Hive and Spark, SPJ or the concept at least, was already implemented. Back then it was called bucket join. And I feel it's not as well used because it was like not very flexible. And I'll explain a little bit how that used to work. So before, you would have to, when you create the table, define certain columns, and these would be bucket columns. And every time you insert a row into the table, you would hash the value of the bucket column and then find the appropriate bucket, right? You would modulo the total number of buckets you wanted and find the appropriate bucket to put. That way your data is kind of laid out according to the bucket key. And when you do a join based on the bucket key, which is called bucket join, you would find the corresponding like pairs of buckets on both tables and then just join them, right? There's no need to shuffle data, right? So, okay, that's great. But what are some drawbacks? Well, first, it's just very inflexible in that, one, the bucket function is hard-coded, right? And this in itself caused a lot of problems, actually. There's a well-known bug in Hive and Spark where the bucket functions don't match, hence bucket tables on both sides can't be bucket joined with each other. Secondly, in the new world, like Iceberg, I think a lot of use cases now are kind of like, streaming use cases. Data is coming in a more time series fashion. And that's why Iceberg has all these kind of newer date-time partition transformations that are much more natural to lay out on disk, right? But it's kind of either or. You can't use those ways to lay out the table for bucket join. Like you have to lay out by the join key. And so these two are already kind of inflexible. There were also like some other ones as well in the initial version that made it inflexible. For example, join key needed to be exact. You needed to know exactly what join key you had, right? Like if you had two bucket keys, to benefit from this, you would need to both join by both keys. You can't change your mind and join by one key. Number of buckets, you need to know how much, like pick a number ahead of time. You can't like, usually people tend to scale that up as the data grows more. But in this case, both tables need to have the same number of buckets. And on that similar vein, skew was a big problem, at least in the initial versions, where if you have one huge bucket, that would kind of slow down the entire join if you execute a bucket join, because there'd be one join task processing that particular unit of work. So that's why in Apple, my colleague Chow partnered with Ryan Blue and some others to make data source v2. And as part of that, to abstract out the concept of bucket into a general thing in Spark called partition transforms. So you may know data source v2 as the kind of interface where Iceberg now plugs into Spark, right? So as part of that, they made the partition transform interface. And as part of that, they abstracted out the concept of bucket join to call storage partition join. So now no longer are you limited by partitioning by bucket. You can now partition by any way you want. All of these like Iceberg partition transforms, like as I said, date-time transforms much more naturally. And now you don't have to choose. You can use them for both, joins, like to reduce shuffle in your joins, as well as just, more natural to fit other query patterns, right? Let's take a look at the first implementation at Apple, again by my colleague Chow. So now you can see, like in this example, I have two tables partitioned by an Iceberg partition transform, day. Some of you may use this one in your job. Now, this can actually use SPJ if you enable two flags. On the bottom is the flag for Iceberg. It's called preserve data grouping. This flag is telling Iceberg all the splits that you return to Spark must now be aligned by partition value. And then on the Spark side, if you enable v2 bucketing enable, Spark groups the splits by partition value and then aligns them and then does the join. So you see on the right side, kind of these final group partitions are grouped by partition value. So you have May 14, 15, 16 on both sides of the table aligned. And now no data needs to be shuffled. Spark can just spawn one join task per unit of work and go ahead with the join. So that's the first implementation. Soon after, Chow did a follow-up. So in the bucket join world, you really didn't have this problem that much where you had missing partitions, I feel. You didn't have missing buckets just because normally the number of rows would just be so much more than the number of buckets that you specify that you typically, because of the bucket is a kind of a pseudo random hash function, you don't have a missing bucket, right? But in this scenario, it's actually much more common. Now that we open the can up to using any kind of partition transforms, it's very common now to have missing days or years on, or days or hours on one table versus another. Especially, Iceberg enabled merge into row level operations, right? Those typically you merge a much smaller delta, maybe daily delta, into a much larger table that's the entire history, right? So that obviously will have many missing partitions on the small table side, the delta side. So then the feature that Chow did as after follow-up was to add this feature, push parts. It's enabled by this flag, push part values. And what it does is each table now looks at the other table, and if there are partitions that it's missing, it will make an empty partition where it's missing, and then the SPJ can continue as is. So I think this flag in our observation is really useful for all use cases. I just recommend everyone to enable it. We're going to look at, we're going to enable this as default in 4.0. Okay, so the third thing Chow did is skew handling. So if you remember, this is the problem where back then it was bucket. Now, same thing here. One partition is just so big that if you just ran the algorithm as is, that processing that would just take too long, right? So the idea here, if you remember, I said there's a two-phase grouping, right? First, Iceberg returns splits aligned by partition value, then Spark groups them in the normal algorithm. So here, if you enable this flag, the way skew handling works is Spark does not group the Iceberg splits. In fact, so in this example, say for example, May 15th partition had a lot of data, and Iceberg, because of the split size, returned us 3 splits. So what Spark does is it takes the other partition on the other side, on the other table, and actually clones it to replicate to match each of these splits of the big partition. It's done this way to guarantee that all the matches can be found. So then you now have 3 tasks processing this big partition versus 1 before. And do note that a lot of people get a little. This flag, to be honest, is not the most clearly named flag. It's a kind of very technical, based on Spark implementation and stuff. But it is kind of useful to know what it means, because a lot of people we see enable it and are a bit surprised to see sometimes, hey, why after I enable SPJ, data is getting read multiple times, or there's more tasks. Do note that this won't slow down your job if you have enough resources, but it may not be necessary for all the cases, right? So you do enable this when you need, if you have a skew, particularly. So then I'll talk about some of the improvements that I'm excited to share, like that we made after those initial ones. So as I mentioned before, so when I first got into the project, I looked at the other side of the coin, right? So SPJ really is dealing with distributing inputs of the join, and I started to take a look at the join implementation itself, and we noticed that the default one in Spark, sort merge join, if you just use the default settings in Spark, it's not as bad as the shuffle phase, but the sort it is bad as well, right? In that by default, I think Spark spills a lot to disk when it sorts, so you're not spilling the entire kind of like table to a network like shuffle phase, but it is still very expensive, right? You spend a lot to disk. So we kind of recommend everyone to use shuffle hash, and this algorithm you actually don't need to shuffle you don't need to sort either side. The way it works is, if you remember from the join classes or database classes, one side gets into a hash map in memory, and then the other side iterates through looking up for matches. What I did here was enabling it for some of these newer Iceberg queries, like merge into, because actually those, as I mentioned before, remember, it's like a outer join, right? So how do you do outer join on a hash, like an algorithm, right? Outer join means you have to return rows that are not matched by the other side. So this idea came from Chung in the Spark community, who implemented for full outer, and I followed up by implementation for one side outer. The way it works in my example, I'm iterating through the T1 on the left, looking up matches on T2 on the right. And if every time I find a match, first thing I do is I mark that I found the match in T2, and then I output to the result as normal algorithm would. But then I do a second pass, because it's outer, to find unmatched values in the hash map, unused in this case, and then I output that as well. So this is a fix that we did, and now merge into a statement should work with shuffle hash join. Cool. So going back to SPJ, we wanted to really release SPJ with all the features that the original bucket join was lacking in the first cut. So one of this important feature is enabling more flexibility in the join. So sometimes you have set of partition keys, but you don't want to necessarily join on all of them, right? In this example, T1 is partitioned by 2 keys, ID and day. T2 is partitioned only by 1 D, the ID, right? And then I want to join by that ID field. So the feature that I worked on was, if this behind this feature flag, allow join key subset of partition key, what I do is I group the table where the partition key is more than join keys by the join key. Because if you think about it, that's the key that's used in the join, right? Where the scope of finding the matches. So in this case, all the ID equals 0 partitions get grouped into a bigger partition. One get grouped into a bigger partition, and then align with the partition on the other side. And then SPJ can run as is. So this is a feature, kind of new feature, and it will release in the next version of Spark, Spark 4.0. And yeah, the second to last feature I added. So this is an uneven number of buckets. And let's just dive into the example to see what this means. So when you create the table, right? I mean, bucket is still supported as a partition transform. You can specify number of buckets, right? If you use bucket transform, and logically, if one table has like 4, one table has 6 buckets. You kind of know intuitively you can do SPJ between them. And so what I did actually is I kind of like tried to make a general solution, and I introduced this concept of a reducer function in the Spark, where if you apply it to the output of a partition transform based on another partition transform, you can get compatible partitions. So let's just illustrate the way by bucket example. If you work it out, it's the greatest common denominator between 4 and 6, and you take the modulo of that on all the bucket values. So here we're modulo 2 on the bucket value. So on the left side, buckets 0 and 2 map into 0, buckets 1 and 3 map into 1. On the right side, because there's 6 buckets, 0, 2, 4 map to 0, 1, 3, 5 map to 1. And now with these kind of bigger group partitions, we can align them and do the SPJ. The reason I made it into kind of this generic thing is I really wanted to extend it for Iceberg. So right now, this interface is merged into Spark. I think it will release in 4.0, and we'll implement it as a follow-up on the Iceberg side. And if this works, I think we can also support all kinds of compatible partition transform. For example, day and hour. One table partition by day, one table partition by hour. You can think that the table partition by hour, if you just reduce it by the day part of it, you can align it as well to benefit from join without shuffle, SPJ, right? And finally, the last one I'll go over today is auto shuffle one side. And this one I think is really a killer feature in that if you've noticed before, SPJ works well if both sides are Iceberg tables and partition tables. But in the real world, there's a lot more complex joins that people want to do. And it'd be cool if we can use SPJ to reduce shuffle where we can, right? If, like, for example, one side is Iceberg table, one side is output of something else, right? And so the feature that we did, so I worked with Jia Fan in the community. So he implemented the initial idea, I implemented it for Iceberg partition transforms, is that one side you can have a shuffle and one side is Iceberg partition. And the way it works is we take advantage of the fact that Spark Shuffler has a pluggable partitioner interface, and we copy over the partition values from the Iceberg side over to the shuffle side, the map of the partition value to partition ID, kind of the ordering. And then for the shuffle side, we first apply the other side's partition transform to get the partition value, and then look up the map to see where we should align it, right? So then it works out to be on the shuffle side, you can actually get your data partition in the same way as the other side, and then do the SPJ as is. And I really think this is very useful. This one is, the patch is out, it's in review, and hopefully it'll be in the next few versions of Spark. So thanks, that's a lot of detail, but we're really excited to share all these new SPJ features, everyone. And I'll hand it over back to Himedri to explain how this stuff is used in production.
Thank you, Jihan. This was very informative. Let's see a practical example of all that Jihan explained, right? We look into an incremental process with, through this, we will see how SPJ triggers in both enrichment, join, and merge into scenarios. This process first reads an Iceberg table incrementally, which is bucketed, and then transform it with join and window operations, and then writes into a final table using upsert. Currently, we need to introduce an intermediate write to the temp table, as SPJ needs 2 Iceberg tables for the merge into. So this makes this process a 2-stage process. Next. In the first stage, we read the incremental data, and next please. Using spark.read.table and apply a filter. Then we read again another table. Next, please.
Hey,
that also.
Hey, Sean, are you sharing your screen? Because we don't see anything.
Yes, sir. Sorry. Are you able to see now?
Yes, now we can see it.
Okay. So in the first stage, we read the incremental input data using spark.read.table. Then we read the dimension table using same spark.read.table, apply filter. Then we join those two tables, select certain fields, and then we apply window operation on the bucketed column. Finally, we write this data into an append mode into Iceberg table. This is a temporary table, right? Now let's look at the plan SPJ with SPJ. This plan, how that plan looks like. From the Spark plan, you can observe that there is no exchange, right? Both the join stage and window operations have no shuffle. Typically, when SPJ is not triggered, you will notice an exchange node in between, where the Spark shuffles data between nodes to co-locate data based on join keys. Shuffle creates many-to-many connections between executors, and many times shuffles are the primary reason for job failure, stage failures in your Spark job. However, in this SPJ case, there is no shuffle. First, Iceberg aligns the data splits by the partition spec. When join keys are part of the partitions key, SPJ either combines or clone partitions based on the join key. Once the partitions are grouped by join keys, Spark scheduler simply spawns as many tasks as group partitions, and executors executing those join tasks reads all the data from one specific partition. This eliminates the need for the exchange step. Also notice that window operations on the bucketed column had no shuffle. Now that the shuffle problem is solved, what is the next intensive operations in this plan? Is the sort in the sort merge join. Although the data from both sides of the join is local to the task, those still needs to be sorted before merge. You may be thinking, can we remove the sort? Next. Yes. Previously, Jian explained the benefits of shuffle has join in the SPJ context. By providing additional parameters, you can hint Spark to do shuffle has join instead of sort merge join. This will remove the sort from the plan. As of now, we need to tweak many parameters to enable this behavior. These are the set of parameters that we worked for us. You may not need all of these. To do shuffle has, Spark needs to fit one single partition of one side in memory on each task. So it estimates whether it can fit it by dividing the total size of the table by number of shuffle partitions. Even though in SPJ, this should be determined by the Iceberg partitions. We plan to investigate fixing this in the subsequent release. Shuffle has join is good in many cases when SPJ is triggered, but creating hash table is too costly operations, right? So sort merge join might work for your case also. Having said that, we should be able to make the enabling shuffle has join more intuitive in SPJ in future enhancement. Next, please. The next stage in this pipeline is the merge into, where we take the temporary table data and merge into the final table. Spark will need to do a full outer join because there are not and non-matched conditions are there. We already know that we need to enable shuffle has join in this case. Let's take a look at the plan for this too. This is the simplest merge into plan possible. As you can see, there is no exchange, no sort using shuffle has join. Merge into tasks are completely parallel, works with the local data. There is no dependency on other executors or tasks on data. Each task now updates or inserts the data in the underlying storage. It runs like a local process. Can we improve even further? Yes. You may have noticed in our incremental process example, we are having to write an incremental data into Iceberg table for the merge into to benefit from SPJ. This is an extra step. Even though the overall job is more stable, consumes way less resources, we can eliminate this extra write if SPJ can intelligently partition one side of the join by using the join key in the merge into. This feature, as Jihan explained, is called auto bucketing. This will solve this problem. Incremental process would be even more efficient. This feature is in progress in OSS. Let's look at the table definition and the Spark properties next. These are the table definitions for the tables involved in the enrichment join phase. The first table, the input driving table, is partitioned by the months and the bucketed by the primary key column. The second table, which is the temp table, has the same schema as the final table where we are offsetting the data. It is partitioned by the primary key column alone. We do not have write distribution mode property specified in because it defaults to hash. The target file size by bytes property do not have much of an impact here in the merge into case. One task handles the data for one bucket, hence each task should create one file only. When the size of the group partition the task is handling is greater than this value, then only it will need to create multiple files per task. Next. So these are the properties that we used to enable SPJ. This is for future references. You can take a look at it later. Now that we understood how enabling SPJ with shuffle hash join works and how to simplify your enrichment join and merge into Spark plan, let's look at some comparative results next. So we measured the CPU and memory for multiple runs of a job using different configurations: without SPJ, SPJ with short merge join, SPJ with shuffle hash join. The input for the job remains same in couple of 100 gigabytes across different runs. You can see from the graph that the utilization of CPU shown on the left and the utilization of the memory shown on the right both drops when SPJ is triggered. Using shuffle hash join improves the results even further, running about 3 times more efficient than the job runs without SPJ. Here is more detailed results from our sample runs. We have also captured like other important parameters to enable SPJ's impact on the Spark job. As you can see, the total runtime reduced, which is a relief, almost by 50%. Each executor is doing less number of tasks. The number of tasks reduced by 12-fold with SPJ. Another notable difference, which was very important for us, is max memory per pod. It is 24 gigabytes for the same input and output in case of SPJ with shuffle hash join, which means that you can configure around 12 gigabyte less per executor, reducing the overall memory footprint of the job. This is a big relief for memory intensive jobs. Another parameter which we looked at is the failed tasks. Failed task causes job to run longer. Sometimes it can cause job failures too. The times when SPJ was triggered, there are no failed tasks. Without SPJ, there are 134 failed tasks. Like this is an average number, considering multiple runs. When we looked at the failure reasons, we saw that most of them or all of them were fetch failed exceptions. We also captured the network activity for these 3 cases and noticed significantly less network bandwidth usage in the SPJ cases. Overall, we can conclude that with SPJ triggered, we have more stable, faster, and efficient job. Next. Let me cover some of our learnings from this exercise. We observed that adaptive query engine interferes with SPJ. Hence, we had to disable it. Write distribution mode, which defaults to hash, is a good optimization to control number of files. For merge with SPJ, this value needs to be set to none. And we recommend set it using the Spark property, not as a table property. By default, Spark writes to Iceberg have a final shuffle by partition key to reduce the number of files. With this shuffle, Spark tries to align the partitions with the task, reducing how many files each task has to write. However, with merge with SPJ, it directly controls the number of tasks, driven by the number of buckets or partitions, grouped partitions. In this case, tasks are already aligned with partitions. So we even have an opportunity to remove this shuffle from the right. When SPJ is triggered, the data is already partitioned, and each task knows how many partitions or which partition it is working on. Hence, the number of shuffle partition has no impact on the SPJ case. Even though SPJ eliminates the heavy process of moving around data via network, the local sort is still expensive process. So try disabling short merge join and enable shuffle hash join. One of the other important observations that we have is if a dataset is consumed for enrichment and or produced by the upset operations, then that dataset can take advantage of SPJ in both upset by the producer and or joined by the consumers by adding a bucket on the primary key in the Iceberg tables partition spec. Next, please. This slide shows the current status of all the important features of SPJ. The green check marks highlights the functionality that has been completed, and the gray ones are in progress. All these features are required for SPJ to work well in all the use cases. For example, uneven number of buckets. When you are not a producer of the enrichment dataset, then you cannot control the number of buckets on the enrichment join. Even though you can control the number of buckets on the both sides of the join, then also you might need to specify different number of buckets based on the size of the data. Hence, in real-life use case,
Hey,
go ahead.
Himadri. We also want to make sure we have some time for questions. Do you know how much more you have on this?
2 minutes.
Okay, all right.
Yeah. We often encounter uneven number of buckets scenario and then feature came out from our use case. Auto bucketing is also an use case where you can remove that intermediate temp right, and this will also help in n-way enrichment join, where table 1 joins to table 2 and then again joins on table 3. The auto bucketing will be able to reduce or restrict the shuffle on one side only. Intelligent partitioning and one other features we are discussing how to enable SPJ more intuitively. We'll come back next with more details on it. Now to summarize, we talked about our Iceberg and SPJ use cases. Then we deep dived into SPJ, various improvements. Then we looked at our real use case with results and learnings. Overall, SPJ is very promising feature with Apache Iceberg and Spark. We are super excited about it, full potential to make the job more stable and efficient. We are looking forward to developing and enhancing SPJ with Apache Iceberg for us and the community. That concludes our talk. Thank you for your time. We are open to questions and we are also hiring, so please contact us if you are interested.
Awesome. All right, let's go and get to some questions here. We got a few minutes, so a lot of SPJ questions here, so I'm going to try to get through it. So the first question over here is, we've had a lot of issues getting SPJ to work with our queries. It seems to require a lot of custom property settings, etc. Is there a good form for debugging this?
Yeah, I mean, definitely we can speak to that, Imagery and I, when we're trying to set this up, and for other users as well. I think it's on, yeah, I think one thing we did notice is that if you enable logging, Iceberg does say if it, so there's something called key group partitioning. So if you look in the logs for this phrase, like key grouped partitioning from Iceberg logs in the Spark job, then you know the Iceberg's reporting to Spark that it is supporting something that could be eligible for SPJ. And I think most of the times, so that's one thing. The other part is, I think most of the time, just double check the configs. A lot of people have typos in config, or they see some config that should be true or set to false. There's another one that kind of interferes, I think, like require partitions or something like that. That's mentioned that should be set to false. Some people set to true. I think the error in config is usually the most. So I think to iterate fast, you could just set up a notebook, kind of like do the explain on the query and try different flags and make it work. But definitely we hear you, and it's on the roadmap to try to enhance it by making additional logging. I think Spark Planner is notoriously black box. I think that's kind of the unfortunate thing there. But we're going to try to enhance logging on this.
I just want to add one more thing here is the auto broadcast threshold, right? Many times you just ignore it, maybe disabled it and that is one of the things you should also look at it, right?
Yeah, that's for the shuffle hash join. That was also a marathon to get that to work. But yeah, the auto join broadcast threshold, some people like for some other reason disable it. So if shuffle hash join is the issue there, you can set that to -1.
Okay, great. Another question. We got about 3 minutes left here. Is there a handy way to validate if SPJ did trigger or not? Any keyword to look into the plan?
Yeah. So there isn't enough logging. So if you're looking for logging, there isn't much except for the key group logger that Jihan explained. Look at the plan. There should not be any exchange till the time, like it's like before the write, you might have exchange, as Jihan explained, that you can still remove that write using some properties of distribution mode equal to none and stuff. Other than that, till that point, there should not be any exchange. That's the only thing you can find out for SPJ. Jihan, you want to add?
Yeah, I think Himadri had one. I think if you just look again at the slides, he gives an example of the plan without SPJ. Basically, you have 2 nodes going to a sort merge join or any kind of join, and typically you would have exchange before, and you just won't have it for SPJ case.
Okay. The next question is, will SPJ combine with partition and bucketing when used together to allow better task splits?
Maybe I'm. So yeah, I think that is the point of SPJ. Maybe I'm misinterpreting the question, but I think yeah. So SPJ does yeah. So in most cases, as we were mentioning in the talk, I think the number of tasks is the same as number of partitions, except in cases where the skew handling is there, or you have the special cases where you need to group again by join keys or group again by the minimum number of buckets, things like that. But typically in a normal scenario, yes, the number of tasks is the same as number of partitions. I hope that answers the question.
Okay, great. I think we're roughly in the top of the hour here. So once again, thank you guys all for joining us. Once again, Himadri and Shizlan, thank you guys for a great session.